welcome to the Skiffy and Fanty Show and our latest episode of SF at School.
They say our solar system is centered around the sun. 9 planets large and full parading by. But somewhere out in space, there's another shining face that you might see some night up in the sky. Interplanet Janet, she's a galaxy girl, a solar system miss from a future world. She travels like a rocket with her comet team, and there's never been a planet Janet hasn't seen. No, there's never been a planet Janet hasn't seen.
So, John, I'm really sorry, but at some point this show, the taglines used to just be like little short quips, and then some point it became a musical. And so that's where we are now.
Neither you have no idea what I was doing.
I don't.
John?
No, afraid not. Sorry.
There was a show. Anyway, we should introduce people before we talk about it.
Okay.
That's Shaun. I'm Paul.
And this is our guest today, who's here to talk about the solar system, John Moores. Welcome, John.
Thanks so much for having me. Great to be here.
So, John is the York Research Chair in Space Exploration at York University. He is the author of nearly 100 academic papers in planetary science. That is a lot of papers, by the way. Just want you all to know. I know how academic publishing works. That's a lot of papers. A+. And he has been a member of the science and operations teams of several space missions, including the Curiosity rover mission. John is also the co-author with Jesse Rogerson of Daydreaming in the Solar System, Surfing Saturn's Rings, Golfing on the Moon, and Other Adventures in Space Exploration, available now from MIT Press. It's described as a thrilling journey through the solar system that merges imagination with hard science. We're excited to get to ask a lot of very strange and weird and fun questions about solar systems tourist attractions.
But before we get to the questions for John and pepper him to death with what we have to say, a reminder to please share your questions and comments with us on social media or at skiffyandfanty.com/listener suggestions. If you aren't already, you can join us on Twitch for Shaun's Alphabet streams every Friday on 7 p.m. Central to be part of our interactive live streaming format show. You can also, if you don't mind, please share to review and spread the word about our ridiculous show, including my musical renditions. Help support us through our Patreon and be part of our Torture Cinema polls, live watches, and other special Patreon-only events on Discord.
So before we get to the questions, I just got to note, Stephen in chat has already borrowed your book, John, from the Toronto Public Library.
Bonus!
That's wonderful. So let's start with some small but kind of strangely presented questions, just to kind of get us started. So, really simple one. What is the solar system?
Ooh.
Wow, Shaun.
Everything really basic here, So the solar system is the sun and the collection of all of the things that orbit it. So we think about the planets, but there's, asteroids, there's comets, there's a lot of dust. If you live in a place where it's really clear and you can see what's called the zodiacal light after sunset, that stuff counts too. So yeah, lots of material, but the planets usually steal the show.
So then,
well, okay.
Well, hold on, Paul. These are my silly questions. Let me get them out. So where is the solar system?
Ooh, and more astronomical question. So this one's hard for me because, I got into solar system stuff through engineering. So, we're in the Milky Way galaxy. We're out in one of the spiral arms. We're closer to the edge of the galaxy than we are to the center of it. That's probably the best that I can do.
That's fair. Here's a silly one. When is the solar system?
So the solar system's been around for the last 4.5 billion years, and the universe has been around for something like 14 billion years. So, we're sort of towards the end of the calendar. Been around for a while.
And then following that would be, how is the solar system?
I should have seen this one coming, I feel.
John.
Yeah, how is the solar system? Well, it gets on as it can, you know, everything's going around in you know, a circle or an ellipse or something like that, and you know, pushing and tugging on one another. We've got some planets that have some atmospheres, and you know, they do their thing. So, you know, it's an exciting and dynamic place. Lots of stuff happening.
And then the last one, which I suppose is the most weird philosophical one, which is why is the solar system?
Goodness, goodness. You know, part of me wants to say anthropic principle because we're here, but uh,
That's weak.
but you know, you put things together in different combinations, and pretty much, you know, as an astronomer will tell you, there's a version of everything out there. So why not one of us?
I like that answer. All right, Paul, I turn it to you. You can now ask a question. I had to get my silly ones out.
Well, this is kind of silly, kind of poignant, kind of putting John on the spot. John, a very deceptively simple question. How many planets are there in the solar system?
Oh.
You know I had to go right there, Shaun. As soon as you signed me up for this show, that was the first question that came to my brain.
Well, I'm in
But
Canada.
I think John's a good short.
Yeah, I'm in Canada, so I'm gonna go with 8.
No Pluto, huh? Okay.
I love Pluto, but Pluto, not like the others. It's its own thing.
That's fair. That's fair. But can I? Okay, I want to ask one more silly one because I have to. Which one's your favorite of the 8 planets that are there? Which do you like the most?
You know, I get this one a lot. And often the question says, you know, you can't pick Earth. So since you didn't say that, I'll pick Earth because, you know, it's really convenient for me. It has air that I can breathe and water that I can drink. It's much more fun and easy to get around and do interesting things on it. So you know, if you want to re-ask with Earth, you know, prohibited, I can go again.
Well, you can go again. I'm fine with that, but I think that's a perfectly suitable answer too, because to be honest, the Earth is pretty darn cool.
But I am curious in the non-Earth answer.
Yeah, then it becomes a little bit of, you know, choosing between one's children a little bit. So a lot of my work I do on Mars. So it's the place I know the most about. You know, I enjoy it. It's got this sort of exotic kind of character to it, but you know, every so often you'll get a flash, you'll edge, and it'll remind you of home, even though it's really cold and the air is really thin and it's carbon dioxide and you can't breathe it. But it's like, you know, gee, I can imagine setting up a lawn chair right there. And then there's other places. I like the upper atmosphere of Venus. It's the most Earth-like environment in the system. And I'm an atmospheric scientist, so I love the idea of, you know, a balloon or a cloud city or just seeing that skyscape. So I think those are probably, you know, my favorite spots.
I think those are both great and interesting spots. Venus is. I was talking with my students about because we were talking about like where the word Terra comes from, and then naturally we ended up on terraforming. And everybody talks about Mars. That's like the place they go, but in a lot of ways, Venus already has like this atmosphere. It's just a bananas atmosphere. And then my students were like, but also if you could terraform Venus, you can fix Earth. Do we need to? And I guess that the answer would be maybe if we just wanna. I guess.
Yeah, it's a question of energy, right? Like Mars doesn't have enough, Venus has too much. So, you know, if you can give Venus a little bit of you know, shade, a little bit of sunscreen, you know, that will, you know, help you there. There's more materials. It's more similar to the Earth in size and gravity and all that good stuff. And who knows, we might need our own shade and sunscreen, you know, in a few years' time.
Very possible. Yeah. So, in thinking about the solar system, you know, you've worked on this book with your co-writer, looking at a lot of the very interesting questions about like what's it like to be on many of these planets. One of the ones that you talk about is Titan, which I've seen kind of get a little bit more buzz because it has an atmosphere of a kind, and it is visually a very interesting moon to look at from at least what I've been able to see. And I was hoping you could talk actually a little bit about what makes Titan in particular such an interesting moon.
Absolutely. So Titan's got a nitrogen dominated atmosphere, same as we do, no oxygen, but it does have liquid methane. And methane is basically taking the same place that water does on the Earth. You get methane clouds and methane rain, you get methane lakes and methane seas. And if you were to go down to the surface, you'd have about 1.5 times as much pressure as you have here on the surface of the Earth. But there are differences, right? Important differences, like it's minus 180 degrees Celsius at the surface of Titan. That's kind of cold. But the atmosphere is also really dense and the gravity is really low. So if you wanted to go flying on Titan, you wouldn't need very big wings to do it. Maybe only the size of a gold eagle, and human-powered flight, you could travel around that way. So it's a really, really neat place for a whole bunch of reasons.
Do you think so? Now I have to ask because you'd mentioned people flying around on Titan. From your perspective, Mars is, I suppose, like the easiest one for us to get to, um, just because I would imagine a part of it is because it's kind of close, relatively speaking. But is it, in your mind, the most suitable place for us to set up some kind of settlement in a hypothetical future? Or do you think there's a better place for us to do so?
I think Mars is pretty good. It is nearby. If you're going to set up a settlement, it's going to be very dependent on the Earth. So being close by is helpful. There are a few things that Mars kind of lacks, but you can make up for that. Uh, Mars is a dangerous place, but all the planets are dangerous places. So Mars is not particularly bad. Clouds of Venus, which is neat, but hard to get down to the surface because the surface is just such an awful place on Venus. So I'd say you're right that if one was trying to set up a big installation on another planet, Mars would be the place to go. Titan, the bus ride is long.
Yeah.
Mm,
We need a better transportation system, I suppose, to get there.
Yeah, definitely.
Paul, do you want to jump in?
yeah. Right. I'm going to go a completely different direction of a question. So, something I've always been curious about. Why is, with the exception of a few things like Pluto's orbit, why is the solar system so flat? Why are all the planets so close to the ecliptic?
So that has to do with the early history of the solar system. You had this, cloud of gas and dust. You had the supernova that came through and stirred things up. And it turns out that when you set this up, the most stable configuration is things that are spinning as a disk. So most of the things in the solar system are spinning in the same direction, and they're quite flat. Things that would have been way off in angle from that at the start might have just gotten ejected from the solar system entirely. So you do end up with these flat disks unless something really bad happens to a solar system. They're all kind of like this.
Okay, that's fair. Follow up. So most of the planets revolve at least relatively the same direction, but a few Venus does not. What's with that? Isn't Venus retrograde or is it Mercury retrograde? One of them
Venus,
is.
yeah, Venus is retrograde, but Venus also rotates really slowly. So it could be that with the combination of pushes and pulls from other planets in the solar system, Venus's day has been, slowed down quite a bit. It's also possible that there was an impact in Venus's past that robbed it of some of its orbital momentum. And there's a few examples of that. Venus is one. Uranus also rolls around the solar system kind of on its
Oh yeah,
side.
90 degrees. Yeah.
Exactly, yeah. So you have some of these peculiar planets, and the people who study this, who dynamicists we call them, um, some of them talk about, well, you could do it with an impact, like a big giant impact, or it could be just the way that it interacts with other planets that currently you have this particular setup.
I guess either one could possibly be true. I mean, you were talking. I was thinking a lot about like Jupiter's impact on the sort of asteroid belt, and what came to mind was like Shoemaker Levy 9, which I was not very old when that happened. So,
Oh, I
but
remember, yeah, the comet plunging into Jupiter, yeah.
and leaving, at least temporarily, scars that we could see with a telescope, which is astonishing to
Oh
think
yeah.
about. And I remember like hearing them talk about it in the news about like, well, the gravity of Jupiter contributed to tearing that thing apart, which puts into mind just how much gravity there actually is out there. And so I suppose then in thinking about the structure, there's like a weird sense of cosmic order in our solar system that has, as you kind of suggested, emerged over millennia.
Yeah, absolutely. And we see evidence of that in the asteroid belt. So if you have an orbit that is a multiple of Jupiter's orbit, so what we would call in resonance, then those particular objects essentially have been kicked out of the solar system. Those are zones where Jupiter's influence is very strongly felt. And there's this thing that happens in early solar system history when you have a lot more of the small bodies. You can have what's called giant planet migration, which I love. It's such an evocative term. But you can have the big planets in the solar system move around, and what they're doing is they're having interactions with billions and billions of asteroids and comets. And as they toss those things out of the solar system, they lose a little bit of their orbital angular momentum and they move around a little bit. And so we have some evidence of how those giant planets have moved. And even now, Jupiter and Saturn are in sort of this little, setup where they influence each other, but they're in this sort of like unsettled but stable kind of arrangement. It doesn't work this way in all solar systems. When we went out and looked for exoplanets, the first time we started doing that, we found all of these Jupiter-sized planets closer to their stars than Mercury is. And what happened there is probably you formed a big Jupiter-sized planet, and it started kicking things out of the solar system, and no one else was big enough to stop it. So it made its way all the way into the star.
Oh.
Huh.
Well, that's terrifying to think about now, because there could be all of these poor dark planets. There's some early science fiction stories. We just read a few weeks ago a story by Edmund Hamilton called "The Star Stealers," which is like about this planet that's got kicked out of or left its solar system and is like floating through the cosmos, and that it steals stars and takes all its energy and leaves. Right? It's kind of an absurd concept, but now you're just making me think like, well, we got kicked out by our Jupiter. It just flung us out, and we had to figure out how to survive, which is creepy.
Or more darkly, Shaun, the Twilight Zone episode, "The Midnight Sun," where the twist at the end is that the Earth is leaving the solar system, not going into the sun.
Yeah. Is that okay? This is a ridiculous question, but is that a concern that like, is that a thing we have to worry about as human beings on Earth, that like our solar system's going to get a little bit rowdy and toss us into the cosmos?
Probably not. There are changes that happen over cycles with the planets. So Mars, for instance, goes through these cycles where the what we call the obliquity, which is the angle that the spin axis makes with sort of straight up and down with its orbit, moves all over the place. The eccentricity, so how sort of oval-like the orbit is, becomes more like a circle and more like an oval over time. All of the planets are going through these kinds of changes. We call them secular changes. And even the Earth does this too. It gives us ice ages and things like that. So essentially, we have a stable arrangement to the planets. And they all like, push and pull on each other and, shove each other in the playground a little bit. But there's kind of a balance of power there in that no one is in the right position at the right time to kick someone completely off the playground. So, we're stable, but the other planets, have their influence over us.
This may lead.
What
There's a
about
question in chat actually from Steven, which I think is relevant here. He says, "My understanding is that humanity is actually quite fortunate to be alive and doing astronomy at the same time that Saturn's ring exists. When did they form, and when do we anticipate they'll be gone?"
It's a good question. The rings around Saturn are what, the official cop out as a professional scientist is they're an area of active research, of course. But there's different theories as to where they came from. And some of those theories suggest that they're old. Some of those theories suggest that they're fairly new. So the older theories think about maybe you had a moon that had what we call differentiated. So it had separated out, so heavier layers in the center, lighter areas on the outside. And that as that moon got closer and closer to Saturn, it passed what we call the Roche limit, where you can start to tear that moon apart. And you pulled off all the water ice layers, and then the rest of the moon just fell into Saturn. And that would explain a weird thing about Saturn's rings in that they're almost pure water ice. It's really quite weird. And this is something that probably would have happened early in Saturn's history, that when the dynamics were still, getting themselves sorted out. But there's a problem with this. The problem is that the rings are very pure water ice. There's very little contamination from sort of meteor material, asteroidal material, these carbon compounds. And that lack of those materials, if there's no way to clean the rings, suggests that they might be newer. The newer theory has been gaining some traction in the last couple of years. But it has a hard time explaining pure water ice. You need some process that gets just that particular component and excludes everything else. So yeah, if you're looking for a fact, I don't have a definitive one to give you.
But we have a weird mystery here.
Definitely.
But what about the rings of Jupiter and Uranus and Neptune by comparison, which are much smaller than Saturn's? What are they composed of?
Yeah, for those, you tend to have more of these sort of, carbon compounds, some icy material, but they're much darker and they're much thinner. There's less material in them. And in some cases, you can't even see them from the Earth. So Jupiter's rings were discovered by the Voyager probes and the Pioneer probes passing behind the planet, looking back and seeing that forward scattered light, kind of like dust on the windshield a little bit. And with Uranus and Neptune, it was mainly from occultations, stars, being blotted out as they passed in behind. But it seems like, the giant planets all have these types of features.
But Saturn just has the very weird one by comparison.
That's right. It's a big system. I mean, it's not a ton of material. You could easily make it from a small moon, but it's very stretched out. So the rings are like 160,000 kilometers wide, 100,000 miles if you're located in the US. And the vertical scale to them is very small, something like 30 meters, 100 feet from top to bottom.
That's so thin? I didn't realize it was that thin. Wow.
It's such a thin system, but you've got all these particles that are sort of pushing and pulling on each other, doing this dance all the way around the system, and everything from the size of a snowflake to the size of, a large boulder or a small house.
A large boulder the size of a small boulder, right, Shaun? I knew you'd get that reference.
Okay, I want to backtrack just slightly. A little bit earlier, you had mentioned exoplanets, and we were kind of talking about the ones where, like a Jupiter-like planet, a gas giant, like we believe flung everything else out. I'll be honest, I feel like I haven't spent a lot of time looking at exoplanet research in many, many years. So I was kind of curious, from your knowledge, is that a pretty common scenario, or is there considerably variability in the kinds of like exoplanet solar systems, exosolar systems, or whatever they're called, that exist?
Oh yeah, there's definitely variability out there. There's all of these things are recording essentially the history of what happened in that particular solar system. But there are two big branches, one in which the giant planet or planets, sort of make their way as far into the star as they can, and others where dynamically they get caught up somewhere. So in our own solar system, we've got Saturn, we've got Jupiter. Those two interact very strongly with one another, and they can hold each other in check a little bit. And everything else sort of, settles down into places where they're dynamically able to do that. And it's really weird what some of these things happen. When we look at our own solar system and people run simulations of that, in a lot of those simulations, about half of them, you actually see Neptune and Uranus switching places. So even the ice giants aren't immune to this kind of, dynamical dance and pushing and shoving.
Interesting. From a scientist's viewpoint, in exploring, comparing our solar system to what we're seeing out there, how do you kind of make sense of that? Because I can look at it from like a science fiction fan's perspective, and I can be like, oh, isn't it neat? There's Trappist and all of these worlds, right? But you get to do all of this like deep, like, oh, like look at the comparison. So what kind of, from your perspective, do you kind of pull out of all of that data, I guess?
Yeah, I think you get two pieces of data. So the first is in our own solar system, we know, well, I like to call it our local laboratory, in that it's accessible to us. We can run experiments on it. If we want to know something about a particular, planet in a particular place in our solar system or a particular process, we can send a spacecraft out to investigate that. With exoplanets, we have such little data on them, right? We might have the dip in light as it passes in front of its star, its transit method, or we might know how it pulls back and forth on its star, that's radial velocity. If we're really lucky and it's really nice and bright, we might be able to see some of the photons that pass through its atmosphere and get an idea of what the chemical makeup might be in that atmosphere. But really, that's all we get. Like there's this thing I like to do with students and with audiences when I talk to them, and I talk about like all the data we have on Mars and how that would fill all of these servers. We have satellites that have taken pictures that are the size where a pixel is the size of a dinner plate, and then when it comes to to exoplanets, I pull out this historical artifact called a floppy disk. And you can store everything we know about a lot of these systems on one of those things, like a 1.25, 1.25 floppy disk. So, we need the information we get from the solar system to be able to understand places in other solar systems as worlds. But the reverse of that is that all of these exoplanetary systems, they give us the census. They tell us what's common in the universe and what's not common in the universe. And one of the real surprises there is that there's a class of planets that are bigger than the Earth and the terrestrial planets, but smaller than Neptune and Uranus. So these are what we call super Earths. And they're one of the most abundant kinds of planets in the entire universe. And we have no idea what they're like. We have no example of this in our solar system. Is this a place where it's easier to form life, or maybe it's harder, or how does it work with a super thick atmosphere or a worldwide spanning ocean? You're still in the science fiction realm with some of these places, and I love those questions.
I would imagine the gravity would be a big problem there, because the more gravity you have, maybe that affects what kinds of life could even arise.
Absolutely. There are some people who feel that some scientists and researchers who feel that these are better places for life to form because they're a little bit more protected. But then when you think about the Earth and you think what the Earth's been through over the last 4.5 billion years, it's not always been a great time. Maybe life needs that kind of push in that harsh environment and those disasters, that it needed to respond to. And that's the problem with having a sample size of one. We don't know the whys.
So what's the nearest super Earth to us?
Oh, that's a good question. I feel like I need to go into the window next to me and, like search frantically.
I would imagine it's nowhere near close that even imagining getting there makes sense.
Well, yeah, and any star getting to is a problem. The nearest star system is 4.3 light years away. 4.2, I guess, in case approximate. So that brought me to a thing I was reading recently about the closest stars to Earth, and right now it's Proxima Centauri as part of the Centauri triple system, but apparently in a million years there's a star that's going to be only like 2 light years from Earth because it's going to come really close. Gliese 710, does that sound familiar?
I wasn't aware of that, but there is proper motion in stars. They do move around in the sky, and I'm a planetary scientist. I love science communication, so everything leads back to Carl Sagan. And there's a simulation that he runs in Cosmos where he imagines, how the night sky and how constellations will change over thousands of years. And I love that, the idea that it's not static and we're getting this one little snapshot, even though it seems permanent, the sky.
Yeah, just what the north, where the North Pole is in the sky has changed over time. We haven't always had Polaris nicely there. I mean, 2,500 years ago, there was no pole star, really, because it was between a couple stars. And it'll change again as we move through the galaxy and the precession of the equinoxes. I find that fascinating.
Yeah, we're off by 2 zodiac signs, but that doesn't seem to have bothered astrology.
That's true. It's hilarious.
So I want to turn to your bread and butter, your world that it's yours now. You can have it. It's Mars. You've written.
You gave him Mars?
Yeah.
Wow,
John
you're
gets
generous.
Mars. Yeah. Because I totally have a right to give away Mars to you, even though I don't think anybody owns Mars. I assume
Mars ain't the kind of place to raise your kids. In fact, it's cold as hell.
That's true.
There we go.
So you've written a bunch of co-written with a bunch of other folks based on the Curiosity rover on methane in particular in Mars. And I was kind of curious. I was reading kind of the abstract. I'm not going to pretend I understand everything because I'm not a scientist, but it had mentioned that methane can be produced by biological things, but there are non-biological methods for it. And so there, I assume, is a very useful reason for why we need to understand how methane arises on Mars and how methane works there. And so I was hoping you could talk a little bit about that work.
Sure, happy to do so. So in terms of methane on Mars, the thing that makes it exciting is that it shouldn't be there. The lifetime of the molecule is very short on, planetary astronomical type of timescale. It's about 300 years. And so because we see it, it has to be something that's being generated, that's being manufactured in the present era. And like you mentioned, there's a bunch of different ways to make it. You can make it by biology. So, the people who talk about, the hidden cow farms, down in the caves below the surface of Mars, biology. You can make it with hot water and rock interactions. So this is a process called serpentinization. On the Earth, the main mineral that's made like this is asbestos. So maybe we've got hot water and rock that are interacting in the subsurface of Mars. The other one, the least exciting explanation, which is where I started on this methane quest because, I'm a boring person, is that we have about 600 tons of organic carbon that just sort of rains down on Mars. It rains down on all the planets. This is the particles that make up the zodiacal light. They're captured and they fall into the atmosphere. They get slowed down really quick and they end up on the surface. And that organic carbon's got to go somewhere. So you've got all these different sources. The question is, what's actually happening and why is it that methane is there 1 minute and gone the next, and it's near the surface, but it's not in the upper atmosphere? There's something about Mars that we don't understand. And that's, I think, what methane really is really screaming about. It would be great if it was biology. Then there'd be a whole bunch of new questions we could look at.
Mm-hmm.
We don't have a lot of measurements, though. I mean, it's a hard measurement to take. So for the Curiosity rover, we only measure it a couple of times a year because it's resource intensive. And, the rover's got other stuff to do as well, of course. There's a lot of science it's collecting. So to see sort of the pattern of what's happening, you build that up over years. And it turns out methane is more complicated than we thought, because we thought we could do it with a measurement or two a year. Really, you kind of need to measure it like every hour, like we do pressure and temperature and other, weather-related variables.
So we need another rover whose job is primarily methane detecting.
Exactly. And as the new owner of Mars, I hardly recommend that we do that.
Well, that gets me to a question of how we conduct planetary science, and we've moved towards at least for the moment, I have no idea what's going to happen with this administration and its priorities towards a robot-based approach towards exploring the planets. And I was wondering what your thoughts on the ROI of that versus a human trip, say, to Mars, as far as getting good science and getting data and getting information out there. Is it robots all the way down for the future? Is that the best way to go?
Yeah, robots versus humans.
Robots versus humans.
This takes me back to parties in grad school. This is, we're all nerds. This is what we argue about. And if we have some astronomers there, we're both wrong. It should be telescopes. Fundamental questions of the universe. So I think they both have their place. Human beings are exciting. It gets people fired up. It makes them want to, invest in space exploration. And as I think we argue in the book, if you are there as a human being, you get to use your five senses and you get to experience sort of the story of that place, and you can come back and have it live in human culture, which we felt was a valuable thing. In terms of, dollars per unit of science, then you've got the robots with a big advantage. Partially, they're cheaper because, they don't need to breathe oxygen, and they never need to come back because they have no friends on Earth that they need to see again. So you've got that advantage to them. They're much cheaper per unit of science. And the science can be much more considered because they don't move as fast. So you think about the amount of, you do a comparison. Astronauts have to move really fast in order to, because of the cost of having them there and the cost to get them there. All the science needs to be done really quickly. And they can do it better because they have better situational awareness. But for a rover on Mars, which is kind of, where I've done a lot of work, you have time. You start the day, you take some pictures, maybe you do a few measurements, and then that data comes back and you get to think about it. And you get to talk about it with your 100 best friends working with you on the mission. And you get to decide, okay, what's our next move? And then the next day you do that next move. Whereas if you're an astronaut on the moon, it's just, bang, 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 right? You've got to, only a certain amount of time in your EVA. If you see something unexpected, you can ask a question back home, but you've got to keep moving, right? Whereas it can be more considered with a robot. So I think that is one of the unsung parts about it. But I kind of feel like you need both, right? Like when you've got that human exploration program, it also creates interest for the robotic exploration program as well. So there's a role for both there.
A chess match versus a soccer game or a football game in Canada.
Yes.
They both have their place.
Yeah. When it comes to Mars in particular, this is probably I would imagine the world we technically, other than Earth, the one we've explored the most. I assume so, just because I've been alive now for, I think, most or all of the robots we've actually put on Mars at this point, I think. Because I don't think we put robots when I was like a little kid. I think it was just like satellites and stuff in space.
Yeah, 76 was the first one, the Viking landers.
Oh, okay.
Viking 1
Though
and 2.
I'm not that old then. Okay.
Viking 1 and 2, I mean, which Sagan worked on.
Oh, okay. That makes sense. I guess like what is it about Mars that you think makes us all so fascinated with?
I think it's that familiarity, right? Like you look up in the Martian sky and you see clouds. You can watch a sunset. You can look at, a scene and you're like, oh, I'm right there in that red rock desert. But there's this principle in marketing of, you want things to be different enough, but not too different. And so with Mars, there's the sunset. Oh, but the sunset is blue. That's interesting, right? There's the clouds, but it's in this reddish sky, and they're behaving a little bit differently, and then that red rock desert, and then you realize, oh, that's on another planet. So I think those things capture the mind. And there's a lot of good science to be done there because it's fairly easy to get to the surface. And Mars shares some of the characteristics of the Earth. You don't have rocks that have been sitting out for a billion years on Earth. You can't look at, a lake bed like we're doing in Gale that's 3 billion years old from a different era. It's actually kind of interesting with the Viking landers. They were a life detection experiment, and they weren't able to detect life. And so, people were a little bit bummed out by that. We didn't go back, for a couple of decades until we sat down and we realized, look, if we want to know about a time on Earth that's hard to sample here, this is the place to do it.
Does Mars? It must have seasons of some description.
Oh, yeah.
Well, what are seasons on Mars like?
So Mars is shockingly similar in terms of its seasons to the Earth, in that the orbital tilt of the axis of rotation is very close. So the Earth is like 23 degrees, Mars is 25. Also, by the way, Mars has a day length that's 24 hours and 39 minutes compared to the Earth's 24 hours. So when we work on Mars, for the first little piece, we stay on Mars time, which does drive most people completely bonkers.
I was going to ask about that because it moves you through the day as a result.
It does. It's so weird. I'm getting myself off track here, but I remember doing Mars Times ops with Curiosity back in 2012 at JPL, and I would drive into the JPL parking lot. Huge thrill, by the way. Even a scientist, like there are things we don't get used to. And normally when you go to work, there is an object that's in the same place in the sky every time you drive in, and that's the sun. But for Curiosity, we were moving around the clock by 40 minutes every day, and you make a complete transit all the way around the clock every 35 to 40 days or so. And so there was an object in the same place in the sky almost every day, but it was the moon. It wasn't the sun.
Oh,
so weird. Yeah. So it's fascinating. Mars time ops I could talk about a lot, but let me get back to the seasons just for a second here. So Mars does have seasons. They're a lot like the Earth's seasons, and you end up getting this seasonal cap of carbon dioxide ice that gets laid down on the winter pole, all the way down to maybe 60 degrees north, 60 degrees south, depending upon which hemisphere's winter it is. And you see this pattern in orbital images, and it seems kind of strange, but the Earth, of course, does the same thing. We have this thing, a lot of it here in Canada, called snow, and that also deposits out onto the surface in the wintertime and gives us this this seasonal cap of material that evaporates in the spring. And the seasons, they last a little bit longer. The seasons in the south are a little bit more extreme because of the the ellipticity, the ovalness of Mars's orbit, but it's very recognizable, I think, to the Earth.
Does it then have like storms as well of what we would see as
Yes.
storms? So does that mean something like
Yeah,
the Curiosity rover or any of the rovers? Those are considerations you have to take into account?
yeah, Curiosity is in good shape. So we do have a dust storm season that happens, and sometimes those dust storms get themselves so worked up that they go global, and those are the global dust storms. Curiosity is nuclear powered though, so it looks at the sky and laughs when that happens. But definitely our solar powered rovers have had a hard time when the skies darken because it can get very dim under those big palls of dust. And the Phoenix lander, which visited the Martian Arctic up at 68 degrees north, it only lasted 150 days because it got cold and then it got frozen in. It got encased in ice and it
Oops.
did not survive that winter.
Wow. I hadn't heard so much about Phoenix. It didn't get the play of Curiosity and the long-lasting rovers.
Yeah, it was a short mission in 2008. It lasted 151 solar days on Mars, about the same number of days here on the Earth. Whereas Curiosity's been going on since 2012. And it's a bigger mission. It involves more scientists. So on the science and operations team at any one time, there's something like 450 of us on Curiosity. And on Phoenix, there was maybe somewhere between 100 and 150.
Wow.
Wow.
Does it have an expected endpoint for its operation? Like, at what point do you guys like, bye bye, like we're done now?
So I can't permit, or sorry, I can't predict, and the demise of Curiosity. But over time, that nuclear battery is going to, lose its ability to produce power, which means that we can do less and less each year as time goes on. And there are mechanical parts on the rover that wear out as well, and that essentially reduces what we're able to do with time. Eventually, you get to the condition where the rover is going to turn probably into a ground station.
Interesting. I like that you started with "I can't permit." By the way, because I prefer that answer. I can't permit it. Like, it will not happen.
Well, I love that the nuclear battery is powered by plutonium-238. Its half-life is 77 years, so I'm hopeful that we can keep on going with this one for quite a while to come.
That is a long time for a piece of technology that we expect to get quite a lot out of.
I mean, look at Voyager 1 or Voyager 2 particularly, which is they're still trying to keep it going as it approaches the heliopause.
And it's so simple too. I mean, we say nuclear battery, right? And that you imagine people in lab coats with Erlenmeyer flasks and whatnot. Plutonium-238 has one useful property. It's hot, and it stays hot. And that's like it. You are basically hooking up a thermocouple backwards to it and using it to generate power. And so that's a very robust system to it. And it's really great for Curiosity because the amount of electrical power that you get is not a lot. So when we
I was going to ask
launched,
how much? How many watts does it get?
yeah, like 100 watts
Oh,
when we
good.
launched. It's like a light bulb, but we can use that really well. So for science and for things we want to do, we can store that in batteries. But because we're only using like 8% of the energy that comes out electrically, what the rover does, which is really clever, is it runs a fluid loop up around the RTG, the radio thermal RTG radio thermoelectric generator, and that thermal loop, that liquid loop, comes down and it keeps all of the instruments in the body of the rover warm. So you get that for free, which is nice.
Oh, that's pretty
Nice.
cool.
I started off in engineering, so I always appreciate some elegant design.
So how did you go from engineering into planetary space science?
Well, I always liked chemistry and physics and all of that stuff. So and I loved astronomy when I was in high school. But I came up to my undergrad, I decided, you know what, I want to do something useful, with my time. So engineering, that was the thing. And I went into engineering at the University of Toronto. and I went into aerospace and space systems. I learned a little bit of science. I was tempted. And as I got into my final year, we had a course where we were asked to design a rover for Mars, actually. And the folks who were teaching it said, let's make this realistic. And there was a NASA announcement of opportunity out there for people to propose rovers into into NASA. And they said, design according to this thing. So we did. But this was being taught by folks in the engineering faculty. We were engineering students, and they didn't talk about science. And what we realized as we were doing this design, well, gee, kind of matters whether we're going to the North Pole or we're going to Valles Marineris or whatever. So we decided, you know what, we need to make like a shadow science subsystem, we called it. We're engineers, right? So I remember really enjoying putting together that science subsystem. And I kind of liked it a little bit better than the engineering side of things, which was that was my hint. That was my gateway drug, I think, there a little bit. And when I learned a little bit later that the scientists get to use the robot, the engineers get to go and make another robot, which, I'm sure that's fun too, but the scientists are the ones who get to do the exploration. I was kind of hooked. And so I found a graduate program that focused in planetary science, but that, embraced the idea of having, engineers as part of the group that they were making. They wanted something interdisciplinary. They wanted all of these disciplines interacting. And I just loved it, and I haven't looked back. And I found it to be really, really helpful, because any planetary exploration, you're living at the intersection of that technology and that science. And if you know both of them, then you've got such an advantage moving forward.
You would think that would be more prized, I suppose, because if you think of something like NASA, it is a massively interdisciplinary organization. There's people doing literally everything under the sun. I mean, also that's literal because you're under the sun.
We're all under the sun.
Sorry. Yeah. It is kind of interesting because I remember I've taught like professional communication courses before, and trying to point out to people, like, sometimes you're going to be in a room and not everybody has the same degree as you, and you have to figure out how to talk to people who maybe have a different background. And NASA's the example I've used a lot, where you could like be talking to somebody whose primary interest is business because they're not the science side of things. They're managing the PR, for example. But you could also be talking to somebody who's an engineer or a planetary scientist, or I don't know, the bazillion different things, a biologist, I don't know, the xenobiologist. So it's kind of exciting, actually, when I think about it. It'd be really fun to be in a room with like a bunch of people with 8,000 different degrees.
Comms is so important. You need to be able to talk to other people in the language that they understand. And there's a role in this for people who are, dyed-in-the-wool engineers, and people who know their planetary science super well, or their astrophysics or what have you, and they've done that deep drill down in there. But you need a few people who can be sort of the glue that bring these people together. And I've always enjoyed those kinds of roles. I mean, when I was working with the Canadian Space Agency, advising the president's office there, it was so lovely because I'd get to work with the engineers and the scientists, the people who did, like missions for Earth science, like Earth observation stuff. And then all of the political staffers who wanted to know why it mattered, but didn't really, for them, their jam was not, the technical details. So having to tailor a message to all of these different audiences, I love that as a problem to, to figure out.
It's a good problem to have, because if you've got all those people in the room, that means a lot of different people are paying attention to you.
Oh, yeah.
We have to wrap pretty soon here.
I got
you,
one
Paul,
question.
You got one last question, and then we will wrap.
It's a fun question. All right, because I see the scarf. Who is your favorite Star Trek character?
Oh, goodness.
Yeah, the symbol's been staring at me this entire episode. It's like, okay, so who is it? It can be any show, any Star Trek property. Go.
Okay, so I grew up watching the original series, the reruns on CBC on Saturday afternoons up here, and a lot of people my age are fans of the Next Generation, but I kind of feel like my series, give it this will date me, um, is Deep Space Nine, and I just loved everybody on that particular cast. But there's one that I have to mention because I put out, I remember putting out a paper, like one of the biggest papers in my career, and NASA commented on it on social media, and people then came and made comments on it. And one of the greatest thrills of my career was when the actor or the actress who played Jadzia Dax commented positively on this description of work that I had done. So after that, she is clearly my favorite character.
Excellent choice.
That's a great choice. Well, I guess the big question we'll start with to end us out is what are you kind of working on next that you can tell us about?
Well, I'm hoping to do more books. For those who know the rhythms of academia, I'm coming up on another sabbatical now, and hoping to do another one of these things. I want to talk a little bit more about methane, I think, in that book. Not just what's going on Mars, but there's so many facets to this stuff having to do with climate change on the Earth. The greatest mass extinction in human history was due to having too much methane in the atmosphere, and our exoplanetary colleagues, they look at methane to understand the climates of other planets and other solar systems, and it's not doing what it was originally expected to do. So this is a very simple molecule, a very simple gas that in some places, like on Mars, it's a proof of life. But in other places, like here on the Earth, maybe it's a destroyer of worlds. So I want to explore that dual character.
Oh, you could do a whole book on methane. And oh man, you could, I don't know, I'd read a book about methane because I bet you I could learn some stuff and it would make me appreciate it more than just when my kid farts.
I'm definitely using that line in my book proposal to my publisher.
There you go.
And where can folks find you if they want to find you in your work?
So I've got a website, johnnymoores.com, that you can go and visit, and that should launch you off in any direction that you want. I'm at York University, and all of our contact information is available up there as well. And we academics, we love it when people reach out when they've taken a look at our work and they want to engage with us. So always happy for conversations.
Well, John, thank you very much for taking the time to
this was
come
fun.
talk to us. Yeah, this is great.
Well, thanks so much for having me. It was delightful.
All right, well, for folks at home, that is the show. If you'd like to let us know what you thought, or you could actually reach out to John and actually ask any questions that you didn't get a chance to ask if you weren't here live with us. Or you can send us an email if you just want to let us know what you thought about the episode. That's skiffingfanty@gmail.com for us. We have a Discord. You can yell at us on Discord. We're on Blue Sky, Threads, Mastodon, YouTube, a whole bunch of places. skiffingfanty.com/skiffythings for all that. And then if you're not here live with us at the moment, remember every Friday at 7 p.m. Central, we're on Twitch at the Alphabet Streams channel, and you can find us there. And we have a Patreon, patreon.com/skiffyandfanty, where you can give us all of your money and your firstborn children. Me personally, I am at ShaunDuke.net. I'm obviously here at Alphabet Streams Wednesdays and Sundays, 6 p.m. for games and other shenanigans. And yeah, you can find me on the internet.
And you can find me, Paul, ubiquitously on the internet as Prince Justin, PRINCEJVSTIN, from book reviews to streaming to everything geeky that under the sun, photography, what have you. Throw a rock and you can find my stuff on the internet.
All right, as is required by the Skiffing Fanty bylaws, I must end this by making it happy. And so with that note, it happened earlier, but I haven't officially announced it, but I will be sending a certificate to John as the new ruler of Mars, population 0. And so you'll be able to do as you please with Mars, which I assume will be just a boatload of scientific research.
Thank you very much.
You're
I'm
welcome.
happy to accept this honor.
All right, folks. On that note, happy ending and scene.